This is section 20 of the ACT manual. This is page 161, Geometry Tactics. There is quite a bit of geometry on the ACT. 20 to 30 questions out of the 60 will deal with geometry. The tricky thing about geometry for most students on the ACT is that, number one, a lot of this material was covered a few years ago in 8th or 9th grade, so some of it is rusty. Number two, there is quite a bit of knowledge and material that was covered in geometry, all those proofs and theorems and shapes and formulas and all that stuff. So the geometry can be tough for that reason. There's a large body of knowledge required. And then the last reason is that ACT does like to combine a lot of geometry concepts in a single question. You may see a question that tests the XY coordinate plane and circles and triangles and tangents, and there might be 4 or 5 concepts all mixed together that can make seeing what ACT is testing quite difficult. So what the geometry tactics are all about, they are just that. They are tactics to get you out of, or get you past, or get you through some of the sticky situations that you're going to find yourself in on geometry questions. And some of these aren't really mathematical at all. Some of them are simply about drawing figures or approximating figures. So some of these things you may not need the exact geometry knowledge that the question intends to require. So let's start with geometry tactic number 1. We're going to go ahead and write down right here, if a picture or figure is described but not given, draw it as neatly and accurately as possible. So if a picture or figure is described but not given, you are going to draw that picture or figure as neatly and accurately as possible. So let's take a look at number 48. A square, you can do this along with me. A square in the standard XY coordinate plane has vertices at these 4 vertices. Where do the diagonals of the square intersect? So they're asking us the point of intersection for the diagonals, so we're going to circle that. So there is obviously a mathematical or algebraic or geometric way to do this question. In other words, there is a correct way to do this question. The way that we're going to do it, though, is we're just going to sketch this figure. So I am going to start off by drawing my X and Y axes, and I'm going to draw them as neatly as possible and as perpendicularly as possible. Now I really only need points in this first quadrant because all of these values are positive. So what I'm going to do is I'm going to make tick marks now on the x-axis. 1 tick mark, 2 tick marks, 3 tick marks, 4 tick marks. I'm going to do my absolute best to make sure that they are equidistant, that the distance from 1 tick mark to the next is consistent. And then I'm going to try to do the same thing on my y-axis. So 1, 2, 3, and 4. So looking at that, it looks pretty accurate. Now I'm going to go ahead and I'm going to start plotting my points. Again, trying to be as accurate as possible. I'm going to actually label those points. That's 1, 3. I have a 2, 1. So that one's down there. That's 2, 1. I have a 4, 2, so that one is about there, 4, 2, and I have a 3, 4, so that one is about right there. Hopefully when I draw this in, it will look something like a square, and yes, it's looking something like a square. So that's the square that was described in the figure. Now they are asking me where the diagonals intersect, so I'm going to go ahead and draw the diagonals. That one is a little bit off, so I would erase that one and I would try again because I want to be as neat and accurate as possible. If my drawing's not neat and accurate, then my approximation based on my figure is going to be off. So there's the point of intersection. If I take that down to the x-axis, it looks basically like it's about 2.5. If I take it over to the y-axis, it also looks like it's about 2.5. So my approximation based on my figure is 2.5, 2.5. That's what I am looking for. This is not 2.5. This is not quite 2.5. That's not quite 2.5, but I'll leave that for now since I have nothing better. This is not 2.5. This is 1.5, so that seems like it's very much so off. This is 2.5, 2.5, and if you don't know that 5 halves is 2.5, you can do that in the calculator, so that seems great. And then this is 3.5, which is way off, 3.5, 3. So I'm going to get rid of that. So really answer choice G, although both of these numbers came close, they don't come nearly as close as answer choice J. Again, there is a correct way to do this question. You can do it using midpoints. You can do it maybe with the distance formula, but there's really no need to mess around with a lot of that math because a nicely drawn figure will get you the answer pretty darn quickly. So that is geometry tactic number 1. If a picture or figure is described but not given, you should go ahead and try to draw the figure. We are going to move on to geometry tactic number 2. Okay, so we're going to talk about geometry tactic number 2. First of all, I'm going to be writing some things in red pen here and some things in pencil. Remember, you should generally be using pencil to write all of this stuff. I'm simply going to be using the red pen to keep consistent with the rest of the videos. You will also need a separate piece of paper before we begin. If you have a bubble sheet that you've been given by your tutor, you can use your bubble sheet. Mine is yellow. That's just to make it easier to see in the video. So if you have a bubble sheet, grab a bubble sheet, but any old piece of paper will do. So let's start by writing this tactic. Geometry tactic number 2 is if a picture or figure is given, you can use it to eyeball / approximate angle measures, lengths, and areas. So again, if a picture or figure is given, you can use the picture or figure to eyeball / approximate angle measures, lengths, and areas. That is the key. So just to contrast this with geometry tactic 1, remember in geometry tactic 1, we were running into the situation where a picture or figure was described but not given, and in that case, we were supposed to be drawing the picture or figure as neatly and accurately as possible. Here in geometry tactic 2, we're talking about cases where we actually are provided with a picture or figure. Keep in mind that the instructions on each ACT test will say that the figures are for illustrative purposes only and that they are not necessarily drawn to scale, but 99% of the time the figures actually are drawn to scale, which again means you can use those figures to eyeball angles and lengths and areas. Now, in terms of eyeballing angles, we're going to start there with eyeballing angles. We should obviously talk about some sort of guidepost angles, some sort of fundamental angles. That would include the 90, the 45, the 30, and the 60, which we have here. We should be able to see that this one on the left is the 90-degree angle. This little segment here and this segment here are perpendicular to each other. Now, by the way, if the day of the test you're looking at an angle but you can't really confirm that that angle is a 90-degree angle or that two segments are perpendicular to each other, one of the things that you can do is you can take your bubble sheet, you can lay your bubble sheet down so that the corner of the bubble sheet is right at the vertex of the angle. And if the angle fits the corner of your bubble sheet perfectly, you know you're dealing with a 90-degree angle. If you were to see, let's say, this vertical segment here disappearing underneath your bubble sheet, then you would know that that angle is less than 90. If you were to see this segment coming out away from your bubble sheet, you would know that you are dealing with something larger than 90 with an obtuse angle. But again, if the angle fits the corner of your bubble sheet perfectly, you're dealing with a 90. I'm going to jump to number 3 over here, angle Y, and I'm going to point out that angle Y should be really easy to approximate because it looks like it splits the 90 into two equal angles, which means that angle Y is the 45-degree angle. Half of 90 is 45. And then back here to number 2, angle X. Angle X, you can see that you can divide the 90-degree angle up into 3 equal angles. Each of those, therefore, is a third of 90, which means each of those is 30. That is what X is. And then over here, angle Z, this is number 4. Angle Z looks like it is about 2/3 of that 90-degree angle. 2/3 of 90 is the 60. So again, we should be able to recognize definitely the 45 and the 90. The 30 and the 60 are a little bit tougher, but these are the angles that you will sort of base unknown angles on. Let's do a couple of examples. Now, I'm going to go ahead and work through these, but if you want to pause the video and try them on your own, you can definitely do that. However, before you pause the video, you should know that when you are eyeballing or approximating angles, you should always give yourself the advantage of drawing in a 90-degree segment to whatever the base ray of your angle is. So we've got this base. What I'm going to do is I'm going to draw in that 90-degree segment to that base using the corner of my bubble sheet. And what that will do is obviously will give me the 90-degree angle, and based on that 90-degree angle and what portion of the 90-degree angle this Y angle makes up, I will get a better approximation here. I also give myself the opportunity to use this little angle in here. So again, draw in that 90-degree line and then go ahead and take a stab at angle Y, pause the video, and then come back and join us when you have an approximation. So here's how I would do this. In this case, I'm going to sort of look back at this 30-degree angle on the previous page, on page 161. I'm going to then try to glance at this angle here, and I'm going to say that this little angle here, it's definitely not as big as that 30-degree angle, but it's also not, you know, a tiny portion of that 30-degree angle. So I would approximate this guy as somewhere between 15 and 20, maybe a little bit closer to 15. So that's what I'm going to do. I'm going to approximate that as 15 degrees, which means that this angle Y in here is going to be 90 minus 15. I would do that in the calculator if necessary, but that's going to give me an approximation of 75 degrees. So my approximation for Y is 75. I'll come back and give you the actual in a moment. For example 2, again, you can try this on your own, but before you do, I would here draw in both, let me do this a different way. I would draw in both the 90-degree line at that vertex right there. So I'm going to draw in the 90-degree line there, okay? And then I'm also going to draw in the 180-degree line. In other words, I'm going to extend that base of the angle. I'm going to extend that over here. And now I've given myself 1, 2, 3 angles to work with. So again, go ahead and pause the video, take a guess at what angle X. Keep in mind, angle X is this obtuse angle here. You're going to take a guess what angle X is and then come back and join us. So what I am going to do, I'm going to look at this angle in here, and I'm going to say that that one, I'm going to actually use this as a reference. This was 15. This definitely looks bigger than that 15, but still doesn't quite look like it's 30. So maybe something like 20 or 25 for this guy. I'm going to go ahead and approximate 20, which means that my total approximation for x, when I add that 20 to this 90, x is going to be 110. So hopefully you got approximations somewhere around 75 or 110, maybe even got closer to the actual values, which are, in this case, 74.5 and 112. So if you did get something close to what I got, you got pretty darn close to the actual measures of these angles. If you get within a few degrees, maybe even within 5 degrees, you're probably going to have no problem spotting the correct answer to the question. The vast majority of answer choices on angle measure questions, they're not very close to each other. They maybe are 5 degrees apart from each other. So if you got within a few degrees, like I said, you're probably going to have no problem getting the correct answer, or at least eliminating a bunch of answers. Now we are going to move on to approximating lengths. We've just talked about approximating angles and how to do that. In terms of approximating lengths, this is one of the sort of funniest things that you could possibly do on the ACT, because it's so stupidly easy, yet so few students actually know that they can do this in a lot of cases. What we're going to do is we're going to make a ruler. Now, you can't bring a ruler with you to the test. That is one of the prohibited items, but you can and will have a bubble sheet with you, and that bubble sheet can be used to make a ruler. So here's the way this goes. Now, all of the steps that I'm about to go through are in this box here. These steps really should just be memorized. I'm not going to address this box directly here. I'm just going to take you through all of the steps that are described in the box. So I guess I will be addressing it directly. I take that back. So here's what we're going to do. We're going to start by calibrating our ruler, measuring a known length. Now, we have two known lengths here. We have the 12 and the 16. By the way, what we don't know is we don't know AC. You should also know that the day of the test, ACT will not ask you a question like this. You would actually need to be given additional information in order to solve for the length of AC. They would have to give you an angle measure somewhere or another length. But in this case, we're going to pretend that we just were only given the length of side AB, which is 12, and the length of side BC, which is 16, and we're trying to figure out what this unknown length is. So we're going to start by calibrating our ruler, and the way that we do that is we measure a known length. Now, I'm going to pick the 12. If you want to follow along with me directly, you should do the 12 as well. What I am doing is I'm putting the corner of my bubble sheet right at vertex B, and I'm going to make a tiny little tick mark where vertex A is. So what I have now done is I have calibrated that from the corner of my bubble sheet to that mark is a length of 12. And I did that because I know that side BA is 12, and I just measured side BA. Now what I'm going to do is I'm going to take my ruler to my unknown length. And keep in mind the orientation of the pages might be different for you, but you should be doing the same general thing. So what I'm going to do is I'm going to put the corner of my bubble sheet down at vertex C, and I'm going to make my first mark on this page where the actual, this would be my test booklet. So I'm going to make the first mark right at that place that the 12 tick mark was, and now so now I know that the length from C to that tick mark is 12. And now what I'm going to do is I'm not going to pick my bubble sheet up. I am just going to slide it down until the corner of my bubble sheet hits that tick mark that I drew. And what I'm going to do now is I'm going to make my next tick mark back on my ruler, back on my bubble sheet. And once I do that, I'm going to sort of peel my bubble sheet away, and I'm going to try to find out what portion of this 12 this tick mark is. One of the things that I can do, I'm going to do this. This sheet is a little bit thicker than the actual bubble sheet, so it might be a little bit different for you. I'm going to put a slight bend in this bubble sheet. And the way that I did that is I just folded the corner of the bubble sheet over to the 12 mark, and then I just pressed, let me just make sure you can see that. I'm just going to press right here, and what that's going to do for me is that's going to tell me where a 6 is. This is 12, that's half of 12, so that's a 6. So what I'm looking at here is 6, 12, and I want to know what this is, And I think a good approximation would be something like that. That's about 9 right there. So this guy's got to be maybe a little bit over 10, so somewhere around 10.5 or 11. So what I'm going to do is I'm going to approximate this remaining length as, let's just do 11. Get a nice round integer there, although again 10.5 would have been perfectly fine. So our total length of side AC is going to be that 11 plus that 12, which is 23, and the actual value, the actual length of AC is indeed 23. So we were, if you did get 23, you were right on the dot. And if you got something like 22 or even 24, again, you're probably going to have no problem getting the question correct. So that's how we would measure a length by calibrating a ruler using our bubble sheet. Now, on number 27 here at the bottom, if you feel like you know how to do this the correct way using your geometric and algebra skills, by all means, go ahead and attempt it that way. If you want to try that right now, just pause the video. We're going to pretend that we don't know the appropriate geometric rules here. We're going to pretend that we have no choice but to measure. So we're going to read through the question. What is the area of square ABCD below? Area of the square is what they're asking, so we're going to circle that. So what I'm going to do is I'm going to say, shoot, I don't know how to do this, but I do know that the figures are generally drawn to scale. So I'm going to start by measuring a known length. The only known length I have here is that diagonal AC. So I'm going to put my bubble sheet down along AC. I'm going to make a tiny little mark on my bubble sheet where point A is. So now what I have done is I've calibrated my ruler. I know that that length from the corner to that mark is 6. I'm going to take that to one of the sides of the square. So remember, the ruler is obviously bigger than the side of the square, so I'm going to make a little mark back on my ruler where side AD ends. In other words, at vertex A, I'm going to make a little mark. I'm going to, again, peel this away. I'm going to do the fold technique, which actually should be easier when you're dealing with thinner paper. This is a thicker paper. It's a little bit hard to do this. So what that does for me is that tells me that that right there is about 3. So I am looking at halfway between 3 and 6 is 4.5. So I'm looking at something maybe a little bit over 4. Maybe that would be 3, 4, 5, 6. So I'm looking at something just over 4, maybe right at 4. So my approximation I'm going to make is maybe 4.2. And the area of a square is side squared. So by my approximation, it's going to be 4.2 squared. And I'm going to go into my calculator. I'm going to do 4.2 squared. 4.2 squared gives me 17.64. So that's my approximate area. There's only one answer that is even close. It is answer choice B, 18. Now keep in mind that even if I got 4 as my approximation, I would have gotten 16 as my area. That still should give me answer choice B. If I had gotten something a little bit more, like 4.5. 4.5 squared is 20.25. 20.25 is actually still closest to B. So we have a little bit of wiggle room here. We don't have to get it right on the nose. That is how we would measure something like number 27. Let's move on. I'm going to address this note at the bottom in a second. Let's move on to page 163 so we can see yet another example of how we can use eyeballing or approximating to get some pretty difficult questions correct. Go ahead and take a read through number 44 on your own. Pause the video if you'd like to read through it. I'm going to go ahead and attack it right now. So they're telling us that points O, which is the origin, and O3 lie in the standard XY coordinate plane. Sorry, O3 is up here. Fine, so that point right there, standard XY coordinate plane. Collection of all points such that each is twice as far from B as from O forms a circle, whatever the hell that means. The point root 3, 0 is 1 point on the circle. What are the coordinates of the center? So they want the coordinates of the center. Now, of course, there is an algebraic / geometric way to handle this question, but it is vastly more tedious and for most students vastly more difficult than simply saying, well, these answer choices are possible points of the center of the circle. So what if I just start plotting them and using this little arc that has been given and what the circle would kind of look like based on that arc. And keep in mind, you don't even need to really complete the circle here, especially if you're not great at drawing like I am not. Completing the circle might actually lead you astray. That actually doesn't look too bad, but we're going to plot these points and see if one of them is most reasonably the center of the circle just based on this figure that's given. So root 3 over 2 comma 3 halves. In your calculator, if you do this, I think it comes out to 0.7 or 0.8 or something like that. And then this would be 1.5. So that's going to be somewhere up here, 0.8 comma 1.5. So that's answer choice F. Well, that's ridiculous. It's not even in the circle, let alone the center of the circle. So that guy's silly. 0, 1.5, that guy's there. That's answer choice G. That's obviously outside of the circle. 0, 1, okay, well now we're finally on the circle, but we're still not at the center of the circle, which is what the question wants. So that seems to be a little bit ridiculous. That was answer choice H. I'm going to label that. 0, negative 1, now we got a contender. 0, negative 1 looks like it is smack dab in the center of the circle that is started by this arc and that I have sort of completed the semicircle here for. And then 0, negative 3, that's all the way down here. So again, at least we're on the circle there, but we are definitely not at the center of the circle. This question, which again, for most students, the algebra here, the quote-unquote correct way here, is going to be very difficult. But with measuring, this question is a cinch. I shouldn't even say measuring. It's just with plotting the points and looking, this question is a cinch. If you want to try to do this question algebraically, be my guest. But again, it is much simpler, I would say, for vast majority of students to just do this with eyeballing or approximating. Now, there are a few, before we move on to tactic 3, there are a few notes that you need to keep in mind about geometry tactic number 2 and measuring. The first note is that you might not want to be using measuring as your primary resource on a lot of questions. For instance, on number 27, again, if you know how to do this the right way, if you know that this triangle right here is a 45, 45, 90, or a x root 2, or an isosceles right, there's a bunch of names for it. What you should know is that this is the x root 2 side, so 6 equals x root 2. You divide by root 2, divide by root 2, you get that the side over here is 6 over root 2, and when you square that, you get 18. So if you knew that that was the correct way to do this question, by all means, go ahead and do it that way. You should know, however, that if you are going for a really, really high score and you don't want to make any careless mistakes, you might want to do it this way, again, the quote-unquote correct way. You might want to do it that way and then confirm your answer with a little bit of measuring. If you are really, really going for 100% accuracy on the vast majority of the 60 questions, you might want to use measuring as a backup or as a way to confirm your initial answer. On that note, you should really never be, and this is the note at the bottom of page 162, if a question asks for an angle measure or a segment length and you have a figure, this should really not be a question that you are skipping. Obviously, if you're completely running out of time and you just have to make random guesses on the last few questions or even the last 10, 15 questions, some students are in that situation, unfortunately. But if you do have to take a random guess, just take a random guess. But if you have a few seconds in which to look at an angle, like this angle Y up here, and at least identify that it is less than 90. If you were on a question that was asking you for angle Y and you saw these answers, let's say you saw 74.5, let's say you saw, actually these would have to go in order. So let's say answer choice A was 65, answer choice B was 74.5, answer choice C was 90, and then let's say D and E were 100 and 130. Well, this is an acute angle. Boom, boom, boom. There's no way that these three angles, a right and then two obtuse angle measures,
could be your answer here. So you, at the very least, could get this down to 50-50 without really even doing any very specific measuring. So again, if you really want to scratch and claw your way to the next score level and you want to add a few points to your math score, this is a really good technique to use. You really should not be skipping any questions that have figure. Just at least look at it, make a measurement of a angle measure or a side length, and take a guess. Now, in terms of the marks that you're making on the corner of your bubble sheet, you might want to go ahead and erase them just to be absolutely safe that your bubble sheet is not going to be scored incorrectly. A few marks around the edge of your bubble sheet are not going to really do anything detrimental to your bubble sheet when it's ready to be scored, but you should just erase them. And then finally, you should know that you're going to have to read the room on test day, and what I mean by that is, although nowhere in ACT's literature does it say that you can't make some marks on your bubble sheet, and it really doesn't even say that you can't use your bubble sheet as a ruler. Again, they do say you can't bring a ruler, but using your bubble sheet as a ruler isn't really the same thing as bringing a ruler. The point is that this is a technique you might not want to draw attention to. So if you notice that your proctor is very vigilant and is watching you like a hawk and is maybe sitting right next to you, you might want to wait to do this technique until the proctor walks away or steps out of the room for a moment. Again, just read the room, figure out if the proctor seems like he or she is someone who is going to call you out on any little out of the ordinary thing that you might be doing. Obviously, you could respond that you're not doing anything against ACT's rules, but you don't want to put yourself in the situation where you have to get in a confrontation with your proctor on test day. It's most likely not going to leave either of you feeling very good. So that is geometry tactic number 2, all about eyeballing and approximating. It is a very, very effective technique. And as I said, whether you are somebody going for a very high score, wanting to confirm your initial answers, or you are somebody scratching and clawing your way to a couple more questions correct, this is a very good resource for you.
Now on page 163, we're going to go ahead and do geometry tactic number 3. Geometry tactic number 3 is, you're going to go ahead and write this down. If ACT gives you a numeric value that basically just means a number, for a measurement that has a known formula, write, running out of room here, let me scroll over, write the formula and set it equal to the number that they gave you. So again, if ACT gives you a numeric value for a measurement that has a known formula, you're just going to write that formula and you are going to set it equal to the number that they gave you. Now, some of you may already be doing this intuitively, which is great. A lot of students do not do it intuitively, and it causes them to get caught up or to pause when they shouldn't be pausing. Anytime that ACT does something like this, where they tell you, let's say that a triangle has an area of 12, you notice this is a numeric value, and triangle area is a measurement that we have a known formula for. So what we are going to immediately do on a question like this, after we circle what the question is actually asking and read the whole question all the way through, which I should have done, what we're going to do is we're going to write down the appropriate formula, which in this case is 1/2 BH, that is triangle area. Obviously, this requires that you know the appropriate formula, and for the ACT, you will generally have to memorize most of the geometric formulas as they are not given to you on the test. So we are going to write the formula for the area of a triangle, and we are going to set it equal to that number. Then when we read the next phrase, we can see that they are telling us that the height is h. Well, that is a substitution opportunity. We can do 1/2 b times 8, or 1/2 8b, whatever you want. And then we can simply start cleaning this up. On the left side, 1/2 times the 8 will give us a 4, so that will be 4b equals 12. We will divide by 4, and we will get that b equals 3, and that is indeed what they were asking us. So the base is 3. So again, by getting started, by writing down the numeric value and setting it equal to the appropriate formula, the rest of the steps really just fall very nicely and very smoothly into place. Example 5, if you want to try this one on your own before I do it, go ahead and pause the video. This one says a circle has circumference of pi units. What is the radius of the circle? So again, they have given us, pi is a number, so they've given us a numeric value. We have a measurement here that has a known formula, circle circumference. We are going to write down 2 pi r. You can also write pi d, but since they're asking us for the radius, I'm going to use the radius form of the circumference formula. I'm going to set 2 pi r, the formula, equal to the number that was given. I am then going to start cleaning this up. I want to solve for radius, so I'm going to do this in one step. I'm going to divide by 2 pi, divide by 2 pi, so I get r equals. These 2 pi's cancel. I'm left with just a 1 in the numerator, so my radius is 1/2. That is what they were asking for the radius, so my radius is 1/2. So again, if ACT gives you a numeric value and you need to, you know the formula that corresponds to that numeric value, you're going to want to write down the formula, set it equal to the number that is given, and then do whatever algebra you need to do to extract the unknown. In the first case here, it was the base. In the second case here, it was the radius. But whatever the unknown is, do the algebra to extract that unknown. Next page, page 164, we are going to head into geometry tactic number 4. This tactic is, you're going to go ahead and write this down, draw lines/segments to break up shapes, or that's supposed to be an R, or create new shapes. Draw lines/segments to break up shapes or create new shapes. I'm going to show you a few examples of this down at the bottom of page 164. If you want to try to draw these out, you can. It's not that big of a deal. If you want to just follow along, that's probably fine too. So many times you're going to apply this tactic on triangle questions where something like this might happen. You might be given, let's say that this is 8. You might be given that this is 45. You might be given that this here is 30. Now, there are some trigonometric ways that you can solve this just given these two angles and given that 8. But one of the really easy things that you can do, and I'm going to draw this line in a different color so it's a little easier to see. If you are sitting here saying, well, I don't know the trig, I don't know how to do this that way, so I'm not really sure how, let's say they were asking you, by the way, let's say maybe they were asking you what this side is. That was the unknown. So what you can do is you can actually just drop an altitude, make this a little bigger. You can just drop an altitude right here. And what that does is it breaks the big red triangle up into two smaller triangles, and those two smaller triangles are made up of a 45-45-90 and a 30-60-90. And if you know your side schemes in the 45-45-90, the x root 2, and the x root 3, 2x, if you don't know that, you need to. What you will be able to do is realize that this 8 is the 2x side. The side across from the 30 is going to be the x. So if 2x equals 8, you divide by 2, you get x equals 4. So we've got a 4 here. The side across from the 60 would be 4 root 3. And in the 45-45-90, these two legs are equal because the vertical leg is 4. That means the horizontal leg has to be 4, which means this entire side is 4 plus 4 root 3. So dropping that altitude reveals the slightly easier way to do this, unless, again, trigonometry is really easy for you. Law of sines, law of cosines, all that stuff. Another example of this might be in a question that deals with inscribed or circumscribed shapes. So I'm going to try to draw a circle here. Let's see how this goes. Not too bad, not too bad. So let's say you see a circle inscribed in a square. What you might want to do here is you might want to say, okay, I'm going to draw radii. So this would be, we're drawing these radii. These would be the segments we're drawing. I'm going to draw radii to these 2 points of tangency or intersection. And I've actually just established a very important fact, and that is that the diameter of the circle equals a side. We can see that this length here and this length here are equal. So the diameter of the circle equals a side of the square. And most likely that's going to be the important relationship in a question like this. So there are multiple ways that we can apply this tactic, that we can draw lines or segments to break up shapes or create new ones. And in terms of that second example I just gave at the bottom of the page, you're actually going to add sort of a sub-tactic here, because this is a very common way that you're going to apply geometry tactic number 4, and that sub-tactic is on circle questions. Always draw radii or diameters to points of tangency / intersection. So always draw radii or diameters to points of tangency or intersection. And again, that's what we did down here in this example. We saw that there was a point of tangency over here. The circle and the square were intersecting there. They were tangent to each other there. We saw that there was a point of tangency or intersection over here. So all we did is we drew one radius to there, one radius to there. In effect, we drew a diameter to points of tangency or intersection. By the way, if you had the sort of reverse situation where there was a square inside a circle, you would want to do the same thing. You see that there are 4 points of tangency or intersection, there, and there. And what you would want to do is you would want to draw a radius to there and a radius to there. And now what you have identified is that the diagonal of the square is equal to the diameter of the circle. So on number 39, we're going to apply geometry tactic number 4 in this way. This is a circle question, so what we're going to do is we're going to draw radii or diameters to points of tangency or intersection. If you do want to try this one on your own, go ahead and try it. If you want to work through it with me, I'm going to do that right now. So in the figure shown below, the circle has center O and circumference 60 pi. We should note that that's an opportunity to apply geometry tactic number 3. We have a numeric value given for a measurement that we have a known formula for, so we're definitely going to do that on this question. The midpoint of AB is C and OC is 18. What is the length of AB? So let's actually start by applying tactic 3. Let's write down 2 pi r equals 60 pi. We are setting the formula equal to the number, and now we're going to go ahead and solve for the radius. We're going to divide each side by 2 pi, divide by 2 pi, pi's cancel, 60 divided by 2 is 30. So we now know our radius is 30. They do tell us that AB has a midpoint of C, so C is the midpoint of AB, which means that AB is bisected there. And OC, this segment here from the center of the circle out to this chord AB, is 18. Great. Now we are going to apply geometry tactic 4. We should be able to see that there is a point of intersection there and there. That's where chord AB intersects the circle. And what we are supposed to be doing is drawing radii to points of tangency or intersection. So I'm going to draw 2 radii, one from O out to B and one from O out to A. And once I do that, I'm going to label them 30. since that's what I just found over here. And now what should become clear, what is hopefully becoming clear, is that we have two right triangles, and in each of those right triangles we know one of the legs and we know the hypotenuse, which means that we can use Pythagorean theorem to find the remaining leg. So I'm just going to find AC right now by doing Pythagorean theorem, and the way that I'm going to do that is by writing down 18 squared plus AC squared equals 30 squared. I am going to go into my calculator and let it do the work for me here. Let me clear that out of there. So 18 squared is 324. So 324 plus AC squared equals 30 squared is 900. I'm going to subtract the 324, subtract the 324, and 900 minus that 324 is 576. So I now have that AC squared equals 576. If AC squared equals 576, I square root both sides and I get AC equals 24. Now be careful, that's not what they're asking. They're not asking what AC is, they're asking what AB is. But since we know that AC is half of AB, we know this other, because C is the midpoint, we know that this other segment is 24. So it looks like our final answer should be that AB equals 48. And indeed, when we go to the answer choices, we can see our answer right there. So that is geometry tactic number 4, draw lines or segments to break up shapes or create new shapes. So again, these 4 tactics can be used on very high percentage of the geometry questions. Of course, as is always the case with these techniques and strategies and tactics, if you know the correct way to do the question, if you know the mathematical or the school way or the geometric or algebra way, you might be better served to just go ahead and do it that way. But there are going to be some cases where you run into trouble, in which case these tactics can help you. And in a lot of cases, the tactics will solve the question quite quickly and simply.